So on the big scale of things, I think it's important for us as architects and designers to have some sensitivity about where our electrical energy comes from, what its sources are, and what impacts those will have on our environment. So this is an illustration of a simplified illustration of what a power plant looks like. We're burning coal in this case, so we have these emissions from the stack that are heating water, that are driving a steam turbine to generate electricity that is in an AC form, an alternating current that can then be transformed and in many cases the voltage is upped so it can be distributed out over the grid system. This can also be the source of energy could be natural gas. That's increasingly popular with fracking. We know that fracking has environmental hazards with it. So in either case, coal and or natural gas have serious negative um, effects on the environment. So consider that when you're specifying equipment that's electrically powered. There is the alternate of solar power, but that's from main sources. That is a very small fraction currently, but it's increasing. So with that in mind, we want to take a look at. I just threw this in to give you an idea of the scale of things like a steam turbine in a generator. So this is a steam turbine being assembled, and this is the scale of it. You see these men down looking at it. So there are multiple steam turbines in these power plants that turn motors to generate our electricity. And this is what a turbine looks like. So these hot gases are through, they go through a period of expansion that drives these rotors that creates the shaft power. We're talking about one of the requirements is to understand this idea of hertz, the frequency of our electricity. When we talk about hertz, we're talking about AC power systems. And I've shown you this graphic of three-phase power and single-phase power. In Europe, the peak repeat would be on the order of 50 times a second. In the United States, it would be 60 times a second, 60 hertz cycles per second. I put this one in down here because of the idea that European having different AC cycle and voltage requires these converters that we're commonly, if you've done any international travel, you're familiar with these ideas of these odd plugs, and then they need to convert them to our US nominal voltages of 60 hertz and 110 volts. So this idea between single phase and three phase, one of the principles to understand is that where do we get 110 volts and 240 volts in our residential power supplies? Typically, if we have a range, we'll have a requirement for 240 volts or a air conditioning system. And so the way we do that in single phase systems is there's a neutral wire that runs at 0 voltage, the ground. And if we go from there to the peak voltage, we'll get 110 to 120 volts. And if we go from peak to peak, we'll get 240 volts. And the same thing in three-phase systems, peak to peak will give us, though, 208 volts, and neutral to peak will typically give us 120 volts. And I'm really not exactly sure why there is that difference. What part of the established standard had determined the way that was. In larger buildings, there can be all kinds of voltages up to 480 volts. In factories, even well above that. But these are typically not our active concern. It would be really important for us, though, to be able to distinguish between single phase and three phase services. Here's a way to kind of spot that idea on the pole. This is a distribution pole. Up here are high tension lines, high voltages. They feed the transformers. This is a three-phase system because we have three transformers. And a single phase just has a single transformer on the pole. So you can quickly identify whether three-phase service may be locally available or not. And we're stepping up and stepping down voltages. So in this case, we take thousands of volts up here, step it down to our usable voltages of 120 and 240 volts here. But sometimes we want to go the other way in order to transmit power over long distances. Many times we step up the voltage for transmission because the more voltage we have, the less amperage we have to deliver the same amount of power. So that's the idea of volts times amps. So if we have more volts, in order to deliver the same amount of power, we need less amps. So we can use smaller wires in high tension distribution lines. This is an illustration of how transformers work. So that pole mounted transformer, um, the difference between the windings on one side and the other dictates the step up or step down of voltage. So we can feed in and control the amount of wires that we wind around these cores. This is where AC power is really important because this is moving back and forth. This coil is inducing a magnetic flux through here, and that flux um, can then shifts back and forth and creates another induction in these wires that delivers power off the other side of it. So it's important if we fed this with DC, there would be no change in flux. There would be no way to convert the electrical energy in a DC system. So if we fed this with this DC power, nothing would come out of the other side. We need to feed it with AC power. That's why AC power is so important to us in our electrical supply systems. So we see these transformers all over, and we actually need them. In this case, one of the issues with modern electrical distribution in cities, especially with this idea of global climate change, is to move overhead transmission lines underground so they're protected from wind and storm events. But they require these vaults. And here we're looking at a vault on a commercial building for electrical supply step down to supply the building. Here it is in a residential area to convert that electrical energy. So it's coming up out of the ground, and then it's going out and feeding maybe multiple residences along here. But these have a physical um, existence on our site, and they need to be thought about and be able to be accommodated, and in this case, disguised in some cases. Service drop, um, where the electrical power enters our building are important parts of our discussion. Just like with plumbing systems, the client or customer has responsibilities and the utility has responsibilities. Um, in the case, this is one municipality, but typically most of like National Grid or Western New York's power supply, the utility will take responsibility from the pole to the entrance head of the building. Um, in this case, it looks like the service drop, the secondary service drop, is the responsibility of the customer. That could be in this case because they supplied a secondary pole, but I'm not exactly sure. But anyway, this term service drop is the idea of what comes from the pole to this head or entrance into the building. And I'll try to detail a little bit about this idea of service entrance. So here we have that power coming into the building. This is this is raw power coming in. There's no circuit breakers, no switches. It goes through a metering system and then goes down and enters, in this case, probably the basement of the building to where the power plant panel would be. Um, and these have typical features to them. In this case, here's the power. These are the lines coming off of the building, or excuse me, off of the pole. They're attached to the building physically to hold them from strain. And then this loop, this drop here, the service drop, um, um, allows rainwater to drip off of here and not enter through the pipe. So this shape and configuration is to prevent water entry into this main tube and then getting into our metering system or actually into the panel. So this is working kind of as a trap to moisture. So it's an important consideration. But then with that all comes important things for architects is this relationship to where this enters the building and where we may have windows placed and what the code requirements are for these various features. So that's an overhead service drop. If we have a transformer that's in the ground, as I'd illustrated a couple of slides ago, this is coming up out of the ground and entering the building through the meter and the panel probably on the other side of this. So that's the basically getting power into the building, and we'll pick up next at what happens when we're inside.